30 meters below the Giza Plateau, where the tourists never go, sits a granite box that should not exist. Not metaphorically impossible, but physically awkward. The sarcophagus weighs 23 tons, carved from a single block of Aswan granite, with interior corners so sharp they catch shadows like machined steel. It rests in a chamber 9 meters below the modern water table, its tolerances tight enough that light barely leaks through the joints. The official story calls it the Tomb of Osiris, a late-period ritual shaft built around 500 BCE, symbolic architecture for underground mysteries. But here is the problem. Nobody seriously explains how you lower 23 tons down a near-vertical shaft without cranes, or why you would carve millimeter-level precision into stone that sits underwater in permanent darkness, or how the construction sequence actually worked when the physics barely fits modern capabilities. If the late period timeline is real, it is the most over-engineered symbol ever built. If it is not, the Giza chronology has a crack running deeper than the shaft itself. The shaft drops straight down through limestone bedrock, 29 meters of near vertical descent cut with rhythmic precision. Stand at the top and peer into darkness that swallows flashlight beams. The walls show parallel grooves where tools bit into stone, repeating at consistent intervals like machine striations. Each groove runs vertically, maintaining alignment over the full depth. The spacing never wavers. Official archaeology describes this as incremental excavation, workers chipping downward with copper or bronze tools, hauling debris up in baskets. Standard quarry technique applied vertically. The explanation sounds reasonable until you calculate the spoil volume. 29 meters deep, roughly 2 meters wide, carving through dense limestone. That is 150 cubic meters of rock, roughly 400 tons of debris. All of it had to come up the same narrow shaft while workers descended. No side chambers, no spiral ramps, just straight vertical extraction. Modern engineers who model shaft excavation highlight the bottleneck. Removing material is exponentially harder than cutting it. Every ton lifted reduces efficiency as ropes wear and workers tire. The shaft at Giza shows no evidence of staging platforms or intermediate relief points. Either the builders had a removal system we have not identified, or the official construction sequence skips the hardest part. And here is the detail people skip. The walls are too straight. Hand-cut vertical shafts typically develop drift. Workers cannot maintain perfect plumb over that depth without sophisticated surveying. This one barely deviates, which brings us to the real problem. At the shaft base, water reflects your light back in black mirror stillness. The chamber floor sits below the modern water table and has been submerged for centuries, maybe millennia. Mineral deposits line the lower walls like bathtub rings, marking long-term moisture exposure. The limestone shows that characteristic darkening where water soaks deep into porous stone. The official explanation handles this smoothly. Groundwater levels rose after construction. The Nile water table fluctuates with climate and irrigation changes. Nobody disputes that. But look closer at the granite sarcophagus sitting in this flooded room. Its surfaces show minimal water damage. The corners remain sharp. The interior walls stay flat. Granite is harder than limestone, yes, but it still weathers. It still accumulates mineral scale. It still shows signs of prolonged submersion. Now consider the construction sequence. You cannot carve precision stonework underwater. Tools slip. Measurements become impossible. Surfaces blur. You cannot polish granite to this tolerance while standing in groundwater. That contradiction is what makes the sarcophagus at Giza an engineering puzzle, not just an archaeological curiosity, which means one of two things. Either the chamber was completely dry during installation, requiring massive dewatering systems we have no evidence for, or the granite went in before the water arrived. If it is the latter, the timeline gets complicated. How long between installation and flooding? Why does the box look so fresh if it has been submerged for 2,500 years? You do not install precision stone underwater, but you also do not ignore the fact that it has been underwater for longer than the official construction date suggests it should exist. The minerals remember water. The granite remembers being dry. The sarcophagus itself demands attention. The sarcophagus is 23 tons of red Aswan granite, hollowed to create an interior cavity with walls roughly 15 centimeters thick. Run your hand along the inside corners. They are squared to near perfection, meeting at angles that would challenge modern stone fabricators. The interior surfaces are flat enough that a straight edge reveals minimal deviation, no chisel scalloping, no rough patches, just smooth, consistent planes. Official records describe this as ritual craftsmanship, extreme care lavished on a symbolic coffin for Osiris worship. The late period Egyptians revered precision in sacred objects. Fair enough, but let us follow the physics. This box was carved at Aswan, 800 kilometers south. It was transported by Nile barge to Giza, offloaded, moved to the shaft entrance, and then lowered 29 meters down a vertical hole barely wider than the box itself. That final descent is where the story gets thin. Modern rigging engineers calculate the forces involved. 23 tons suspended on ropes creates massive tensile loads. Hemp or flax rope, the strongest natural fibers available, would need to be extremely thick to avoid snapping. You would need multiple ropes for redundancy, each anchored securely at the surface. The descent would have to be slow, controlled, and perfectly balanced. Any rotation would wedge the box against the shaft walls. Any sudden jerk could shear the ropes. Here is what makes it harder. The box fits the shaft with minimal clearance. There may be 10 centimeters of space on each side. Thread the needle with 23 tons, no second chances, no room to adjust mid-descent. The geometry is so tight that getting it down feels more difficult than carving it in the first place. The granite came from Aswan. That is documented. The quarries there show the same red granite, and ancient Egyptians definitely worked that site. Nile transport was proven technology. Barges carried multi-ton obelisks in tomb reliefs. Sledges and rollers were used on flat ground. So the transport story holds for the first 800 kilometers. It is the last 30 meters where the narrative thins out. No archaeological evidence shows large staging ramps near the Osiris Shaft entrance. The surface around the shaft is relatively flat, with no massive earthwork scars. This means the box was lowered directly down, not slid down a gradual incline. That is engineering problem number 1. Problem 2 is rope anchor points. To lower 23 tons, you need solid rock anchors capable of handling asymmetric loads. Modern simulations show that the most dangerous moment comes in the final 10 meters. If the box tilts even slightly, it binds against the walls. Friction spikes and ropes can snap. Engineering teams who have reconstructed similar descents emphasize that ancient builders were clearly capable of remarkable feats. The issue is not whether they could do it. The evidence shows that they did. The issue is that our reconstructions require technologies or techniques that leave no archaeological trace. Either the methods were so efficient they left minimal evidence, or we are missing something about how the operation actually worked. The transport story stops at the shaft edge. Everything after that point is inference, not documentation. We know the box ended up at the bottom. We just cannot quite explain the middle part where gravity and friction wanted to kill everyone involved, and that is where it gets worse. The precision of the final installation suggests this was not a desperate, barely controlled drop. It was placed carefully. Look closely at those repeating chisel marks on the shaft walls. They catch side light beautifully, each groove casting a sharp shadow that reveals depth and rhythm. The spacing stays consistent, roughly 8 to 12 centimeters between parallel cuts running vertically down the full shaft depth. This is not random hacking. It is systematic removal following a planned pattern. The official tool inventory for late period Egypt includes copper chisels, bronze pounders, and possibly early iron implements. These tools are documented in other contexts. The marks on the shaft walls could plausibly come from those tools, worked by skilled laborers following traditional techniques. But here's the detail that catches modern attention: maintaining vertical alignment over 29 meters of cutting without visible drift. Stonemasons today use plumb bobs, laser levels, or transit theodolites to keep vertical cuts true. Ancient builders had plumb bobs, simple but effective. The question is how you maintain reference when you are 20 meters down in a narrow shaft with limited light and no line of sight to the surface. Modern scanning reveals that the shaft walls show minimal deviation from plumb less than what you would expect from purely manual alignment over that distance. Maybe they were just that good. Ancient Egyptian builders achieved extraordinary precision in other contexts. The Great Pyramid's base level, for instance, is astonishingly flat, but vertical shaft excavation presents unique challenges: limited working space, debris accumulation, and difficulty repositioning reference lines. The straightness of the Osiris Shaft walls suggests either exceptional surveying skill or some alignment method we have not identified yet. Straight down is harder than straight across. Air shafts in pyramids can be checked by sighting along their length. Vertical shafts have no equivalent visual reference. You are cutting blind, trusting your instruments in darkness. The shaft's axis aligns closely with Giza's broader architectural grid. Compass readings show it parallels the pyramid baseline orientation, roughly aligned to cardinal directions with the same small deviation seen in other Giza structures. This might be coincidence, or it might indicate the shaft planners were working from the same master survey that laid out the pyramids. Official archaeology treats the shaft as a late period addition, built around 500 BCE, roughly 2,000 years after the pyramids. If that is accurate, the alignment could simply reflect reuse of existing survey markers or deliberate imitation of older structures. Ancient Egyptians in later periods often referenced earlier monuments, but here's the puzzle. Achieving that alignment requires knowing the underground orientation before you start digging. You cannot course correct a vertical shaft once you are 20 meters down. Modern comparison: vertical shaft alignment is genuinely difficult. Mining engineers use gyroscopic equipment or laser theodolites to keep bore holes true. Even with modern technology, drift happens. The tighter the tolerance, the more careful the initial setup needs to be. For the Osiris Shaft to end up aligned with Giza's surface grid means the planners either had exceptional surveying capabilities or got very lucky. And there is a deeper implication. Surface planning linked to subsurface work means somebody mapped the entire operation before cutting began. They knew where they were in relation to the pyramids, understood the local geometry, and could project that orientation downward through solid rock. That is not simple ritual digging. That is integrated architectural planning at a scale that suggests the shaft was not an isolated project. It was part of Giza's larger spatial logic. Underground work still obeys surface geometry, even when nobody but the builders would ever know. The standard construction sequence goes like this. Excavate the limestone chamber first, creating a cavity at the shaft bottom. Then lower the granite sarcophagus and maneuver it into position. Limestone is softer than granite, so the chamber could be carved with bronze tools. That order of operations makes sense, except when you examine the clearances. The granite box sits very close to the chamber walls, maybe 10 centimeters of gap on most sides. That is tight. Not impossibly tight, but uncomfortable when you are trying to maneuver 23 tons in three-dimensional space. Lower the box straight down through the shaft, and you arrive with it essentially vertical, oriented the same way it traveled. Now you need to position it precisely where it sits today. Physics reminder: rotating or sliding 23 tons requires overcoming static friction and managing momentum. In a confined space, that means multiple workers levering and nudging incrementally, but there is barely room for workers to stand between the box and the chamber walls. If the box needs to rotate, if it came down oriented differently than its final position, the turning radius barely fits the chamber width. The insertion path is geometrically feasible, but just barely. It requires the box to be lowered in precisely the correct orientation, then nudged only slightly to final position. Any significant maneuvering would be nearly impossible, which means the installation had to be planned with extraordinary precision, shaft alignment, box orientation, descent path, and final placement all predetermined before the first rope went around the stone. There is almost no room for error, and yet the installation apparently succeeded because the box is exactly where it needs to be, sitting level and centered as though someone had all the time and space in the world to place it carefully. The chamber's geometry barely allows the operation it must have contained. Those mineral deposits on the lower walls tell a water story. Mineral lines mark where standing water sat for extended periods, calcium carbonate and other salts crystallizing out of solution and leaving horizontal bands that trace old water levels. The pattern is clear. This chamber held water for a long time, centuries at minimum, maybe longer. The official explanation attributes this to post-construction flooding. After the shaft was built and the granite installed, groundwater gradually rose, submerging the chamber. Climate shifts and changes in the Nile water table over 2,500 years could easily account for flooding. Nothing mysterious about wet basements in archaeology, but look below the mineral line. The tool marks on the limestone walls, even those well below the water stains, remain surprisingly crisp. Water and time soften limestone. It is a relatively porous stone that weathers under moisture exposure. You would expect rounded edges on the chisel grooves, blurred details, maybe some surface spalling where crystals force their way into microfractures. That is what happens to limestone kept underwater for millennia, but significant sections of the shaft show sharper detail than the water story would predict. Materials science is clear. Water plus time equals erosion. The question becomes timeline. If the shaft was built around 500 BCE and flooded shortly after, we should see 2,500 years of water damage. If it was built earlier, substantially earlier, and flooded later, the math might fit better. Or if the water table fluctuated dramatically, rising and falling multiple times, the preservation pattern makes more sense. The walls remember water differently than the official timeline suggests. Mineral deposits mark long-term flooding. Crisp details suggest shorter exposure. Both observations are real. Reconciling them requires either a more complex flooding history or a different construction date. Either way, the simple story, built then flooded, does not quite capture what the stone surfaces actually show. The contrast is jarring, rough shaft walls versus a precision granite box. Stand in the chamber and compare them directly. The limestone walls show competent but unrefined stonework, functional excavation, tool marks left visible, surfaces that are flat enough but not polished. Then look at the sarcophagus. Different world. Millimeter level flatness. Corners squared to angles that approach geometric perfection. Interior surfaces smooth enough to reflect light cleanly. Official interpretation attributes this to symbolic focus. The sarcophagus represented Osiris himself, a sacred object worthy of extreme craftsmanship. The shaft was merely access, functional architecture that did not require finishing. Ritual priorities explain the difference, and there is logic to that. Ancient builders everywhere invested more effort in sacred objects than in surrounding infrastructure. But here is the puzzle. Why invest extreme precision where visibility is lowest? The chamber sits 29 meters underground, accessible only by dangerous vertical descent, destined to flood and sit in darkness. No processions would view it. No priests would gather for regular ceremonies. The audience for this precision was essentially zero. Yet someone carved it anyway, not just carefully, but with standards matching or exceeding surface monuments that actually had viewers. Pattern recognition, similar mismatches appear at other Giza substructures. The Sphinx Temple shows different construction phases using different techniques. The Valley Temple's massive megalithic cores do not match the later limestone facings. The subterranean chambers beneath the pyramids sometimes show rougher work than the monuments above. When you see this pattern repeatedly, it starts suggesting different construction phases or different builders working at different times. It feels like two projects sharing one whole. One team excavating access with functional efficiency. Another team is installing precision stonework according to standards that seem divorced from context. Maybe they are separated by decades, maybe by centuries. The contrast is what matters. Rough meets refined in a way that implies the chamber has a more complex construction history than built all at once for ritual purposes. Late period texts mention Osiris rituals and symbolic burials, but they do not describe deep engineering projects. The archaeological record for this period is actually quite rich. Papyri, tomb inscriptions, administrative records. We know what tools were used, how temples were staffed, what festivals were celebrated. Major construction projects typically appear in these records, with dedications, labor rosters, and material inventories. Documentation. The Osiris Shaft appears in mythology, not in engineering documentation. It is described as a sacred site, a symbolic connection to the underworld. But the massive subterranean quarrying operation that would have been required, the logistics of lowering multi-ton Aswan granite, the surveying precision, those details are conspicuously absent from texts that otherwise document far smaller projects with bureaucratic thoroughness. Absent archaeological gap, excavations around the shaft have not revealed clear worksite debris layers. When ancient Egyptians undertook major construction, they left traces, tool fragments, pottery sherds from worker camps, and waste chips from stone dressing. Large projects are messy. The Giza Plateau shows these traces around the pyramids themselves. Worker villages, bakeries, copper tool debris, pottery dumps. Around the Osiris Shaft, the archaeological signature is much quieter, messy. This does not mean the shaft was not built when official timelines claim. Absence of evidence is not evidence of absence. Maybe the debris was cleared more thoroughly, later construction disturbed earlier layers, or we simply have not found the right spots to excavate. But it does mean our confidence should be proportional to our documentation. And for a project requiring hundreds of tons of rock removal, thousands of labor hours, and sophisticated engineering, the paperwork is surprisingly thin. Confidence. Big projects usually leave loud paperwork. Temples get dedicatory inscriptions. Tombs get construction records. Mining operations appear in administrative documents. The Osiris Shaft leaves a mythological footprint, but a whisper-quiet engineering record. That contrast is curious for something this ambitious, mythological. The surface structures directly above show different masonry weathering. The foundation stones, massive blocks forming the lowest courses, display erosion patterns that do not quite match upper blocks added in later periods. Different exposure histories leave different signatures: wind erosion, sand abrasion, moisture wicking, salt crystallization. Foundation stones that predate later additions should show those differences, and they do. Official archaeology acknowledges this openly. The site saw multiple construction phases. The late period builders erected temples on older foundations. Some stonework dates to the New Kingdom, some to the Old Kingdom, some even earlier. This layering is well documented at Giza. Civilizations building on civilizations, each generation adding to what came before. But here is the engineering constraint. Cutting a deep vertical shaft beneath an existing plateau without causing instability in nearby structures is genuinely difficult. You are removing support, creating void space, potentially triggering settlement or collapse. Modern engineers plan carefully around existing foundations when excavating shafts, using underpinning, support systems, and vibration control. The late period builders would have faced the same challenges if they were cutting through already occupied ground, which raises a question about sequence. If the shaft was added late, after the plateau was already crowded with monuments, the excavation becomes riskier. You are threading between existing structures, avoiding underground chambers, managing ground stress. If the shaft came earlier, before major surface construction, the engineering gets cleaner. You can plan around it rather than retrofitting it. The surface tells a story of layers, foundation stones, later walls, later dedications. Something down here might predate the label late period ritual shaft, not because of mystical reasoning, but because the engineering sequence suggests underground work might have preceded some surface monuments. The ground remembers occupancy in layers, not all at once. Similar patterns show up elsewhere. Deep shafts with precision stone installations are found at sites separated by thousands of kilometers. The combination repeats: rough access excavation, refined inner chamber, megalithic stones placed with geometric precision. At Göbekli Tepe in Turkey, massive T-shaped pillars were sunk into bedrock foundations. At Tiwanaku in Bolivia, precisely fitted stone channels sit beneath temple platforms. At Cambodia's Angkor Wat, labyrinthine underground passages connect to central sanctuaries. Official interpretation calls this convergent evolution. Different cultures facing similar needs develop similar architectural solutions. Ritual spaces often go underground. Caves and subterranean chambers feature in religious practices worldwide. The engineering logic follows naturally. If you are building sacred spaces below ground, you prioritize the ritual core over access infrastructure. Hence precision where it matters, efficiency everywhere else. But the stress patterns are remarkably similar. tight clearances, difficult transport routes, alignment challenges, weight management. The specific engineering problems that make the Osiris Shaft impressive also appear at these other sites, not just conceptually similar, mechanically similar, the same friction coefficients, the same lifting constraints, the same surveying difficulties. Modern modeling reveals that when you try to move multi-ton stones through confined underground spaces, you hit the same bottlenecks regardless of location: ground pressure limits, rope tensile strength, leverage physics, human biomechanics. These are not culturally variable, they are universal constraints. Different cultures encountering them would develop solutions within the same physical boundaries. Maybe that is the answer. Ancient builders across continents solved similar problems and arrived at similar techniques because physics does not negotiate. Or maybe there was something else: shared knowledge, common tradition, an older blueprint that multiple cultures referenced. Both possibilities exist in the evidence. Neither requires lost super civilizations, but both acknowledge that these underground precision signatures represent serious engineering, not symbolic theater dressed up as mystery. The physics allow certain facts to stand without controversy. Mass can be lowered using ropes, leverage, and coordinated labor. Ancient Egyptians demonstrated this repeatedly with obelisks and statues. Water management is possible with enough determination, dewatering, drainage channels, and seasonal timing. Alignment accuracy improves with practice and careful surveying. None of these capabilities are impossible. What the physics struggles with is the full logistics stack operating simultaneously. You can solve the transport problem if you simplify the precision requirements. You can achieve the precision if you ignore the water complications. You can manage the water if you accept rougher stonework. But doing all three at once, moving massive granite through impossibly tight spaces, maintaining millimeter tolerances, working around a water table, and aligning with surface geometry, is when the official model starts feeling incomplete. The model explains symbolism beautifully. It accounts for ritual purpose, mythological significance, and cultural context. Where it gets thinner is mechanical specificity. Exactly how many ropes, exactly what anchor configuration, exactly what sequence of operations. Those engineering details often get hand-waved with "they were skilled builders," which is true but not mechanically descriptive. This does not prove alternative timelines or lost technologies. It just means our confidence in the standard story should match the documentation we actually have. Where we have clear evidence, tool types, transport methods, and construction dates, we can speak confidently. Where we are inferring logistics from end results, we should stay humble. Return visually to that granite limestone gap. It is less than 5 centimeters in places where the sarcophagus edges approach the chamber walls. Run a flashlight beam along that seam. The clearance is so tight that shadows barely penetrate. That gap represents the margin of error for the entire operation: lowering, maneuvering, final placement. Everything had to work perfectly because there was almost no room for it not to. Precision hidden where no audience stood. No viewers, no witnesses, just stone meeting stone in darkness. The granite box sits in its chamber. Clearance from the walls measured in centimeters. Flashlight beams reveal shadow lines too sharp for careless work, too precise for symbolic gesture. The numbers fit in stone: 23 tons, 29 meters deep, millimeter level tolerances, alignment matching Giza's master grid. All measurable, all real. But they do not fit cleanly in history. The late period timeline works if you do not ask too many questions about engineering specifics. The ritual explanation satisfies if you accept extreme effort for zero visibility. The construction sequence makes sense if you do not push too hard on the physics of lowering massive stones through vertical shafts while maintaining precision that rivals modern fabrication. The accumulated evidence does not resolve into neat answers. It resolves into better questions. This is not a question of aliens. That is lazy thinking, and it insults ancient builders. The real questions are why the official story feels too tidy, what engineering methods we have not yet identified, and how confident we should really be about timelines based on mythology rather than on construction records. The Osiris Shaft represents something real, an underground chamber containing precisely worked stone, excavated with considerable skill and planned with sophisticated surveying. Ancient Egyptians built it, no doubt about that. The mystery is not who, The mystery is when, how, and why the mechanical details seem persistently harder to explain than the ritual explanations suggest. The deeper chamber is not just below Giza, it is below the story we tell about it. The official version accounts for symbolism and purpose while leaving the engineering half explained. Maybe that is because documentation gaps prevent fuller reconstruction. Maybe the construction phases were more complex than current timelines acknowledge. Maybe late period builders were simply that good, and we underestimate their capabilities. Or maybe when you shine light into underground spaces, you illuminate not just stone but the gaps in what we think we know.